Continuing with our lecture on photosynthesis, we'll take a look at the electromagnetic spectrum and how visible light is used in photosynthesis. The electromagnetic radiation is coming off of the sun. It's produced from all of the chemistry that's happening in the physics within the sun. And the radiation coming off is of different types of energy. It's called electromagnetic radiation. Some of the radiation is called gamma rays, and those have 10 to the minus 5 nanometer wavelengths. Okay, what is a wavelength? Imagine a wave that goes up and down in like a sinusoidal motion, and it completes one wave. The wavelength is just the distance it takes to complete a wave going up and down. And a nanometer, remember, so a meter is about 3 feet, and then a millimeter is 1,000th, and then a micrometer is 1,000,000th, and a nanometer is 1/10000000th of a meter. So gamma rays are 10 to the minus 5 nanometers. So that's 1,000,000th, 1,000,000,000th, and then even smaller than that. And so they're very, very tiny wavelengths. And it turns out the shorter the wavelength, the higher the energy of those waves. And as you continue up into slightly longer wavelengths, you get X-rays, okay, which are very high energy, very short wavelengths. Remember, if we go to the dentist, they use X-rays to look at our bones, and they penetrate through the skin, but they also can cause cell damage, which is why we wear that lead vest. And as you go up through ultraviolet light, and eventually we get to around the, hundreds of nanometers long, and that's visible light. So of this energy coming off the sun, we can actually see with our eyes 380 nanometer, which is purple, and as the wavelength gets a little bit longer, we can see all the way to 750, which is the red light. Okay, remember, higher energy on the left going to lower energy, and then below what we can see is called infrared, and then microwaves or even larger wavelengths. Radio waves are in the meters long, very long waves. Okay, so this is the energy that plants and organisms that are photosynthesizing have to capture. And the energy that they capture happens to be in this visible light spectrum, what we can see with our eyes. And one question we can ask is, why is it this energy that we can see, why is this the most important radiation for life? And it's a really good question. We can see that energy. Plants use it to build sugars. And it turns out the reason is because it's the right amount of energy to raise electrons into higher energy states so that they can form new bonds. Okay, imagine a molecule gets hit by an X-ray. It's such high energy that this electron might just fly off completely, and then we make a free radical, or we could do DNA damage. But if it's visible light, and you have the right molecule, it can accept that energy and just form a new bond, okay, or just energize the electrons stably. And so it's the right amount of energy to stably add energy to electrons, and if you go lower energy, then the electrons don't have enough energy to jump higher energy states that are useful, in building molecules. So in plants, they use what's called a pigment molecule to absorb the light from the sun, the visible light. And here's a couple examples, and this is what gives the plants their color. Pigments are colored molecules. Here's beta carotene, it's a pigment. And these pigments usually have these ringed structures. And it's this ring that the light will hit, and this ring, the electrons here, are able to absorb that energy. Here we have chlorophyll A or B, just slightly different versions of the same thing. You have this long tail that sticks into a protein complex, and this, kind of looks like a vitamin and a mineral. If we remember, hemoglobin had a heme ring and an iron atom. This is like a plant vitamin and mineral. It's chlorophyll A or B with magnesium in the middle, and this is where light's going to strike. And then electrons will be energized, and this magnesium can help move those electrons so we can build, sugars with that. So pigments are colored, and they absorb energy, and they also emit energy. Okay? If we were to take a plant and extract the pigments from it, we would grind it up in some kind of solvent, and then we could do paper chromatography. We drop the plant juice and let a liquid move up through the paper. And what it would do is separate out all the pigments based on their size and their charge. And we notice that there's several bands in leaves. You have carotenoids, which is a pigment that can be used in photosynthesis, chlorophyll A and B, phytophytin, and carotene. And all of these are pigments that can help absorb the energy from light. Now, if we take those pigments and we actually shine light of every color on those pigments, we can see their absorption spectrum, or we can see all the light, the colors of light that these pigments here can absorb. Okay, so if we cut out chlorophyll B and we stick it in a test tube, and then we put this in what's called a spectrophotometer. And the spectrophotometer has a white light shined through a prism which separates all the light out based on its wavelength. Then we can pick every single wavelength in isolation and shine just that color on the chlorophyll, and then measure how much light gets through. If we were to shine green light on the chlorophyll, most of that green light would keep going through, and so 100% almost transmitted through. If we shined a different color, the blue light, then not much of that blue light shone through, it would be transmitted, and most of that blue light would be absorbed by that chlorophyll. So if we do this for the different pigments, and we shine all the colors of visible light on those pigments, we get an absorption spectrum that looks very similar to this, where chlorophyll A absorbs around dark blue, chlorophyll B absorbs highly at a lighter blue, carotenoids absorb at blue, and then notice they all drop off at green and yellow, and they don't absorb any of that color of light. And then all of a sudden they start rising again when the light becomes red. So these pigments are best at absorbing red light and blue light, but not so good at absorbing green and yellow light. Okay? So this kind of tells us why plants are the color they are. If we look at a plant, the leaves are absorbing the red and blue, and they're going to use that energy for photosynthesis most likely. And then the green light and the yellow that's not being used is just transmitted through and reflected out. And that's the color we see because it's the color coming off of the leaf because the plant's not using it. Okay. Now knowing this, this will be a discussion question for the week. How would you design an experiment to test which colors of light are best for photosynthesis?